Okay, that's mean welcome again. This is our second week of instruction, and I will start chapter 2. That's mean, first of all, let's just quickly wrap up the chapter 1, which was the week 1. I think I'm quite happy with all the activities and your participation. Of course, not everybody participate. That means if you didn't participate, if you didn't post any question, any answer on the discussion board, I will really ask you to do this. Okay? Because it's nice to see if somebody is asking a question, you may try maybe to answer or type some comments. Okay? You can maybe find the question and try to type the question, because sometimes you're asking a question and you're not really typing, you're just stating the number, which means we have to go to the particular assignment or to the textbook and find the question. You can use on the discussion board, when you're typing, you can use the little icon, the square root icon. You can hit this, and then this is a tool for you to type mathematical symbols. That means it's relatively easy. You can definitely try, and you will type nicely the mathematical questions. That means, again, thank you for all of the students that pose the question and answer the question. Of course, I'm trying to monitor and I'm also answering a question, but I would like to see you answering the question. And another thing is, because you probably realize I did create on the discussion board like a discussion for a week. And everybody was posting a question, like creating another discussion. I mean, we can still do this, but maybe we'll be more organized if we will keep all of the questions in that discussion thread. Like whatever I create, I think I call like week 1, week 2. That's mean even for this week, I did create week 2 derivatives. And if you have any question related to this week, post in that discussion thread. Okay, that means we'll be maybe a little bit more organized. If you still create a new discussion, it's still fine, but I think it's like lots of discussions, but all of them are related to chapter 1, the week 1. Okay, and one more thing, the average was quite good of the first week quiz, the weekly quiz. That's mean I think, yeah, as I said, I am quite happy. But please work hard, because I'm getting some emails that the class is really difficult. But of course, it's the online class, first of all. And the second of all is calculus. Yes. I mean, calculus could be really easy if we really put the time, if we really, if we are involved and engaged. Okay, that's me. Please remember, and I will try always to help you to make all of the stuff, all of the material accessible for you. Okay, that's me. Let's start. Do you have some questions? Math question, admin question before we start? Oh, somebody can't. You can hear me, right? Because somebody can't hear me. I see on the chat box. Okay, thank you. Because yeah, I've never know if the audio is on. I mean, it is on, but I always a little bit worried. Okay, that's me. No question. Let's start. This week we will start chapter 2. That means half of this chapter will be covered. Today's session, I will focus on section 2.1 and 2.2, which is the introduction to derivatives. And you probably notice I did put for you the recording for section 2.3 and 2.4. Okay, that means you can look at the videos, you can look at the slides and try to learn, try to master the skills, and then take the weekly assignments. Okay, but 2.1 and 2.2 I will cover now. That means what we will have in these sections. You probably remember our first section, which actually was the first live session, and I talked about the tangent line. That means we remember, in order to find a tangent line, we have to find a limiting position of the secant line. Okay? That means we were looking at the slope of the pink line of the tangent line, but we know that slope, we have to compute rise over run. right? We have to have changes in y, changes in x. If we have only one point, we can't really get this. How can I get slope between the point and itself? 0 over 0, right? Which we also know how to deal with this. That means the reason was in order to get the slope of the tangent, I picked another point, Q, but we can see this graph is maybe not really good for our concept because the point Q is really far away from the point P. We have to move it really, really close. Okay, that means that was the idea. And that's the formula for the slope. Let's see what we can do. Okay, that's what I'm saying. Point Q is moving and it's getting really, really close to the point P. And then we will have really tiny changes along the X and really tiny changes along the Y. Okay? But we know that we can't really get exactly the point P. That's the reason that it looks like 0 over 0, but it's not really. It's a tiny X interval or the Y interval. But overall, we call this slope of the tangent line is a limit of the slope of the secant. Okay? And I can write this like that. Okay, that means that's important definition. Slope of the tangent line, it's a limit, and we can see X is the coordinate of Q, and X is approaching A. A, of course, is the point P. And that's the difference. F of X minus F of A, X minus A. Difference in Y is difference in X. That means that's the slope. Of course, we may have a situation that the limit is undefined. Then we will not have it, but let's assume that limit is defined. Then is the slope of the tangent. Okay. Now let's see what we can do. We did this exercise. You probably remember finding an equation of the tangent line to the parabola x squared at the point 1, 1. But what I did, I was approaching point 1 from the left and from the right-hand side, like taking 0.9, 0.5, 0.1, 0.01. Okay? Or on the other side, 0.5, hang on, am I crazy? 1 point on there, let me just draw the number line. 1, and then we have to approach from the right and from the left-hand side. This will be 1.5. Okay. Okay, that means this is my point 1. And I have to approach this. That means 1.5, 1.1, 1.01. That will be the numbers on the right-hand side. On the left-hand side, 0.5, 0.9, 0.999. Okay? And you remember, I did use the calculator and I did compute the slope. And do you remember what was the answer? Do you remember what was the slope of this tangent line? Who remembered the first session? You don't remember? Like we were approximating? No? Okay, I do remember, but okay. Because now what is my point? Since we know that the slope of the tangent is a limit of the slope of the secant, that means I can come after like going through section 1.6 especially, and 1.8, but 1.6, the calculation of limits, I can simply calculate this limit. I don't have to really do the approximation, all of these values. That we can see what we have. Function is defined as a x squared minus 1 over x minus 1, and x goes to 1. That means, of course, substituting, we're getting 0 over 0. But this is good sign for us because 0 over 0 is telling me that we have a common factor we can find out, and that's the common factor gone, and the slope is 2. Yeah? I hope that you remember. Okay, and having slope, no problem. We can use point slope form, point slope, and get the equation of the tangent line. Okay, but we can see now it's easy because we know how the slope is defined, and we have a tool to compute this. Okay, let's see what else I have. I think I also mentioned this. This is the slide from from section 1.4. That means computing a slope of the tangent, we can say it and this will be equivalent. That is exactly the same like slope of the curve. Because if I will draw a curve, And if I will zoom in, the curve becomes almost the same like a line. Okay? And if I draw the tangent line, they are almost the same. We can't see the difference. We can't distinguish the difference. That means computing a slope of the tangent is exactly the same like slope of the curve. Okay? Okay, that means now let's look at the general approach, because of course I'm trying to find some definitions, some new terminology. And of course we know what is the new terminology, derivatives. Okay, that's what we have. Again, the same thing. Pink line, tangent line, blue line, and secant line. Okay, and in order to get, actually I can switch off my video because it's covering the slide. That's the slope of the secant line, but I'm not changing. Okay, I will change. Okay, now I will change a little bit. That means I'm really hoping everybody understand this. Yeah, it's like f of b minus f of a, b minus a, but we have f of x because we have this x value. Okay, now I will change the notation a little bit, and sometimes it's just easier for the computation point of view, or even to understand the whole concept. That's what I will do. I will name the changes along the x, the delta x, I will name h. That means this distance is h. Okay? And if this distance is a, and this distance is, this is a, this is h, then I can say that x is defined as a plus h. We can see a plus h. I can remove from this. Okay? That's what we can see. And that's what I will do. I will replace x with a plus h. That means the only thing that I have to know how far I'm going away from the point A. Of course, h, I'm assuming that it's really, really tiny, almost 0. Right? That means let's replace. Let's put instead of x, a plus h. And in my denominator, if I will put instead of x, a plus h and minus a, of course I can cancel out and I only have h. Okay, that means this, the second box, I can use different color. The blue box represents exactly the same thing, slope of the tangent line to the curve at the point A. That's when we have A and we have H, and we know what H is. H is telling me how far away I'm going, like from A, but we know that we can't go far, okay? That means this is slope of the secant line, but now, I wanted to add, if I will put a limit, I mean the same slope, f of a plus h, which actually, this will be the point f of a plus h, and this is just a plus h. Okay, minus f of a, that's my rise, and that's my run. And if I will indicate that h goes to 0, okay? Now, this is the same definition that we had before, but using different notation. That's slope of tangent. Okay, tangent line, of course, at A. Let me just put A. I don't want to confuse you with the X. Okay. Yeah, that's we probably most likely we will use the H notation. Okay, let's see. Oh yeah, I do have the same thing, but with H, A plus H, A plus H. We can see that's what we have. That's me now. I did copy the original definition, but I also put the new one. Both of them means the same thing, slope of the tangent line. But using the H notation, the second one, and the first one, just the difference. I mean, this is also the difference in Y, it's difference in X, but having X and A, and this one having just H. Okay, that's me. Please note that you know both of the definitions, that you recognize, we have to recognize this. And I can tell you how I can ask you. What kind of question? Okay, let's see what I have. Okay, let's do this exercise. Find an equation of the tangent line to the hyperbola 3 over x at the point 3, 1. That means equation of the tangent line. Of course, the main point of this question is to find the slope. If we have slope, we can use point slope and get a line, not a problem. That means slope of the tangent is defined, right, as a limit as h goes to 0, f of 3 plus h, we know what this means. This is like the value, we're going away h units, minus f of 3 and over h, rise over run. And now my function is defined as a 3 over x, which means f of 3 plus h, I'm gonna evaluate for the given function. Instead of x, I will put 3 plus h. 3 over 3 plus h. And f of 3, I will do instead of x, I will put 3. But this is 1. Okay, and I do have really nice limit. Again, going through the section 1.6, you confident how to solve this type of limit. Yes, we can see how the whole, each section is like a chain. It's like a continuity of the previous one. Okay, that's what I will do. I will multiply both sides by 3 plus h, because that's the common denominator. I will multiply this, and I will multiply the first fraction, and I will multiply 1. That's mean multiplying a fraction by 3 plus h, simply denominator is cancelled out, gone, just 3. Negative 1 times 3 plus h is just this, and denominator I copy. I did distribute negative, that means please note that negative. I am cancelling 3's, okay, and then we can see we do have h, because of course what I had 0 over 0. I should maybe mention that. If I put h, I have 0 over 0, and please remember, most likely 0 over 0, it's not, I mean, it's almost never 0, but it's also not really undefined. We have to find a finite number. We have to find the value that actually is defining. I have a question. Can you move the page over to the right? It is cut off. Oh, you don't see the whole page? Because on my second monitor, I am actually seeing the whole page. How can I, do you see, can you answer my question on the chat box? Do you see the whole slide? Okay, okay, good. That means probably Matthew, right? Matthew is asking. Okay, thank you, thank you. I did switch off the video, of course, because the video was covering. Okay, that means Matthew, maybe it's your settings. Maybe it's your Zoom window. Maybe you can try to, okay, thank you, good, okay. Okay, that means now we can see we do have h and h, the 0 is gone, and I can substitute instead of h 0, and I do have negative 1/3. Okay, that means what we did use the limit definition of the slope of the tangent. We went through and we have a slope. That means now my favorite point slope, substituting point, substituting slope, getting the slope intercept form, negative 1/3 x plus 2 is the equation of the tangent line. And I think I have a graph. Okay. The blue curve is, of course, hyperbola, and that's the slope. Negative 1/3 looks, I think, quite correct. Okay, but what is important for this slide? The whole process to compute this limit. Okay, let's move on. Or any question you may ask, I will always stop and answer your question. Okay. Okay, another thing that I also covered as an introduction last week was the average velocity and instantaneous velocity. Okay? And we remember the average velocity was exactly the same concept like slope of the secant line. Okay? But the instantaneous velocity was exactly the same concept like slope of the tangent line. Okay? Like we have to find the rate of change at one point, the same thing. That means what I have? I can use exactly the same limit to find the instantaneous velocity, like at the point A, at the time A. Like we remember, like I'm driving, for example, and exactly at 1 hour, I want to know what is my speed. That means I will use the calculus concept and I will use the theoretically slope of the tangent line. That we can see what I have. Of course, I have my function f, the position function a, but that's the velocity. That's what is my point. My point is that in order to find the slope of the tangent, we're using this limit. Excuse me. In order to find the instantaneous velocity, we're using this limit. And actually, in order to find any rate of change, instantaneous rate of change, we will use this limit. That means what we have. We do have a special name and special notation for this type of limit. Okay? And possibly, do you know what's the special name of this special limit? The whole limit, I can maybe, I don't wanna, I have on my next slide. Do you know what's the special name of this limit? Yes, we saw a few times, now you don't know. Try to answer, even if it's wrong. It's always nice to have some discussion. No? Oh, I'm sure you are brave enough to type something. What's the special name of this limit? Slope of the tangent. Yes, thank you, thank you. It is derivative. Okay. Oh, I'm sorry, I just... Okay, that we do have a special name, okay? Because one more time, this type of limit, believe it or not, looks maybe complicated, but of course it's not. But it's so widely used in outside, not only in the theoretical math class. It's lots of application. Actually, we can even think we have to find a rate of change at that instant, at that moment. How things are changing, like in science, in engineering, in economics, in finance. We have to know how things are changing. And we really have to define this. That means this is an instantaneous rate of change. That means a special name, of course, is derivative. Okay, I can maybe write it's derivative. That means this is a limit definition of the derivative. And the special notation is because actually this is derivative at the point A. Yeah? You probably, if you had calculus in high school, you probably remember you use x, but I will also introduce this. But for now, this is derivative of the function f at the point A, and the special symbols notation for the derivative is like prime. That means f prime at A means derivative and is defined by this limit. H goes to 0 always, because we can see that's the small difference, the 0 between point P and Q, and f of A plus h minus f of A, rise over run. Okay, that's name, definition and notation. Okay, and I do have the same thing. That means that's from section 2.1, it's extremely important. That's the beginning. That's the beginning of the whole journey about the derivative calculus. Okay, that we can see again, the same limit, that's the notation, that's the derivative. Or I still type the old version without h. This is still the same thing. If you're more confident using that form, we can use that form. But I think this one contains xa, it's a little bit confused. We will definitely stick to this one. Okay. That's me now, let's try. Let's find the derivative of the function x squared minus 8x plus 9 at the number a. Okay? That means what we have to do at the moment, because again, I know that some of the students know some shortcuts. We will still reach the shortcuts, but the point is to know how to use the definition. That means this is my definition. F of a, because that's what we have to know, derivative of the function f of x at a. I have to evaluate my function x squared minus 8x plus 9 for these quantities, a plus h and a. That's what this means. F of a plus h means that I have to take the entire function, and instead of x, instead of every single x, I have to put a plus h. And then f of a means that I have to replace x with a. That we can see. X squared minus 8x plus 9 x squared minus 8x plus 9, the same function, but it's just evaluated for different values. Okay, that we can see. A plus h squared minus 8 times a plus h plus 9. And this is instead of xa. That means make sure that you know how to evaluate a given function for especially a plus h. F of a is relatively easy. Okay, and I'm assuming that when I substitute h, I am going to have 0 over 0. That means I have to really expand everything on the top, find a common factor h, cancel out, and then put h back again. That means I'm going to FOIL this. A plus h squared means a plus h times a plus h. That's this. I will distribute negative 8. Okay, and I will distribute negative. Okay, and now we can see this is gone, this is gone, and this is gone. Whatever stays contains h. I can factor out h, and that I was looking for. The 0 is gone. Now I can substitute instead of h 0. That means derivative at the number a is 2a minus 8. Okay, that means we really have to know this process. Okay, let's see. Now I can actually use this. I can use this. Let me maybe do on this slide. 2a minus 8. That means this is derivative at the point a, and we of course know, because that's how I introduce the derivatives, this also means a slope of tangent. Okay, tangent line. Slope of the tangent line at a. At a. That means, can you tell me now a little bit of arithmetic? If a is 1, can you tell me what will be the slope of this tangent line? If a is 1. If a is 1, I can maybe name the slope m. Thank you, negative 6. Okay, if a is 2, what's the slope? I'm just trying to ask you a little bit of calculation. Yes, negative 4, and maybe one more. If a is negative 3, what will be slope? Yes, thank you. Okay, you know your arithmetic, good. Okay, that we can see now I can substitute any values and I can compute the slope. That means it is quite helpful. Okay, and I think my next question is just asking the slope at a being 3. Okay, that means we have to find equation of the tangent line to the same curve, the same parabola at the point 3, negative 6. Actually, let me come back. What will be the slope if a is 3? I didn't ask you for 3. If a is 3, what's the slope? It's negative 2. Thank you. Okay. Yes, thank you. Thank you very much for your answer. That's what I'm using. Point slope form, substituting a point and slope, of course, is the derivative. And the derivative was, we did use the definition. We simplified to this form, and substituting 3 is negative 2. Okay. That's negative 2x, because the 6 is cancelled out. It's the slope. It's the entire equation of the tangent line. Okay? But again, we did use a definition, derivative as a slope of the tangent line. Okay. Oh, I do have the graph. Nice. Okay, let's keep moving. Did I type the solution? No, but let's maybe do it. Find the derivative of the following function, which is square root of x at 0.11. Okay, that means I have the solution, but maybe I can write with you. That means derivative means f prime at 1. Limit as x goes to 0, f of 1 plus h minus f of 1 over h. Limit as h goes to 0. And now I have to evaluate a function f of 1 plus h. That means this is f of x. Instead of x, I will put 1 plus h. Square root of x will give me square root of 1 plus h minus, instead of x, 1. Nice. Limit as h goes to 0, square root of 1 plus h minus 1 over h. Okay, and again, I have 0 over 0, but I have to evaluate this limit. And I think we know how to evaluate. Do you remember how can we simplify or how can we rewrite an expression with the square root part? Do you remember what we can do? It's a typical simplification. How can I simplify the root expressions? Oh, you definitely know. Multiply and divide by the square root plus 1, which we call a conjugate expression. I'm going to copy the same square root and instead of minus 1, plus 1. And remember, conjugate expression. Limit as h goes to 0. I will just copy the conjugate expression in the denominator because I can't distribute. I have to keep that h because I'm looking for this h to be cancelled out. Okay, but now multiplying two conjugate expression, I can square the first one minus square the second one. Squaring the square root is gone. Squaring 1 is 1. Okay, I can cancel out this, and then we actually see h and h. The 0 is gone. Now I can just substitute 1 plus 0 plus 1. 1 plus 1, 2. Okay, that means the derivative at the point 1, 1 of the function square root of x is just 1/2. Okay. Okay, but again, one more thing that is really important, I would like to point this. Right? The green limit represents the derivative of the function square root because we can see the square root at 1. Because it's important to identify a function and a number. Okay. I have my solution. I did minimize. Okay, I have another one, but I will not go through this one. You can try, it's the same thing. I have another one, but I will also not go through this one. Okay. Okay, the only thing is, hang on. The only thing is, let me just state, because I see my next question, which is extremely important. That means maybe I will not, I just come back to question 7. I will not go through, but what I would like to do, let's just set up a limit that represents the slope of the tangent. That means slope of the tangent line, of course, is the derivative at the point 1. I did copy that value. Limit as h goes to 0, f of 1 plus h minus f of 1 over h. Limit as h goes to 0. Okay, and now my function is x minus x cubed. X minus x cubed. That means instead of x, I will put 1 plus h, 1 plus h. And then minus, that means this is the first thing. And then minus f of 1. What color I can use? That means f of 1 will be simply, you probably know the value, but f of 1 will be 1, not x, 1 minus 1 cubed. Okay, we can see instead of x, I'm just putting 1. Instead of x, I'm putting 1 plus h, and all over h. And then I can simplify, I can simplify. Probably it's not easy to get the answer. Okay, we can expand everything, but the point is to know how to set up a limit. And the same for this one. Okay, limit, which is derivative at 3, always that value, that's the slope of the tangent line. Slope of the tangent line. Limit as h goes to 0, f of 3 plus h minus f of 3 over h. And let's see if we can evaluate h. That means now my function looks like x minus 1, x minus 2. That means x minus 1, x minus 2, minus x minus 1, x minus 2. But instead of x, for the first one, I have to put 3 plus h, 3 plus h. For the second part, I have to put just 3. Of course, I don't really have to have this parenthesis, but just to show you. And again, it's quite complicated fraction, but for me, important thing is that you know how to set up this limit. And this limit represents the slope of the tangent or the derivative. And we still have work to do. Okay, that's me now. Get ready for some questions. I do have a few limits, okay? And each of these limits represents the derivative of the certain function at some number a. And I would like you to state that function, what function you see and what value of a you see. Okay, that means limit number 1. Limit as h goes to 0, 1 plus h to the power of 10 minus 1 over h. That means, what do you think? This limit represents the derivative of what function? Oh, just x? Can you see x to the power of 10? Thank you. That's what I'm looking for. That means this is derivative at a, and function is simply defined x to the power of 10. Because instead of x, we put 1 plus h. Okay, and what is the a value? What's the a value? It's 1. Thank you. That's okay. I can tell you, it maybe looks simple, but it's so important, so crucial for late to move on later. Okay, let's see the second one. Limit as h goes to 0, 1 over 2 plus h minus 1/2 over h. That's mean again, this is derivative. This limit represents the derivative of the function at a. But who can tell me what is the function? Thank you, 1 over x. Really good. And what is the a value? The a value is 2. Perfect. Okay, limit number 3. The limit as h goes to 0, 4th root of the quantity 16 plus h minus 2 over h. That means this limit also represents the derivative at a, but who can tell me what is the function and what's the corresponding a value? Or probably you don't know how to type this function. You can just describe, you can just use the words if you like. Oh? Or maybe you don't know the answer. It's the 4th root of x. Thank you for writing this. 4th root of x. And what is the a value? Oh, x to the power of 1/4. Kristen, that's also good. And what's the a value? Because now we have to be careful. Who can tell me the a value? Oh, it's always this number. Yes, you can see 2, 1. Yes, it's 16. Because this number represents the value of the function at 16, f of a, which 4th root of 16 is 2. 16, not 2. Not 2. Okay, another one. Oh, this is function from calculus 2, but we can still get a function. Limit as h goes to 0, 2 to the quantity 2 to the power of 5 plus h minus 32 over h. That means this is also a derivative at a, but who can tell me a function and the a value? Oh, no, 2 to the power of x. 2 to the power of x. And what is the a value? The a value is 5, of course, because that's the a value. Okay, another one. Oh, limit as h goes to 0, tangent of the quantity pi over 4 plus h minus 1 over h. That means the same thing. This is derivative at a. And what's the function? What is the function? It's tangent x. Thank you. And what is the a value? The a value is, yeah, you can type either yes, thank you, is just pi over 4, because tangent at pi over 4 is 1. Okay, that we actually recognizing, having a limit definition, you're recognizing a function and the number a. That's nice skill. Okay. Oh, I have one more. Okay, really fast. This is derivative at a. And what is the function? Yes, thank you. Is simply cosine of x. And what's the a value? The a value is pi. And do you think, is this my typo or this is correct? Plus. Because we know we're subtracting f of a plus h minus f of a. Minus, 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 minus. And suddenly plus. Do you think it's my typo or it's correct? It's correct. Why is correct? Because the value at cosine at pi, what's the value cosine at pi? Because this is f of a. It's -1, right? That's when I'm subtracting a -1. Actually, I can remove this. Or I can put this 1. That's the reason that it's plus. Okay, good, thank you. Okay, we've done with this. Okay, I do have one question like that. Yeah, let's try to solve it. And then we will jump to the section 2.2, which will be almost the same like 2.1. Okay, find the equation of the tangent line, of course, standard question, of the to the graph of the function g of x at 5. If some informations are given, g at 5 is -3 and g prime at 5 is 4. That's me. Do you think I can give you like maybe 1 minute? And do you think you can try to give me the answer? What I'm looking for? I'm looking for equation of the line, tangent line, mx plus b. Okay, that will be the equation of the tangent line. That's why I'm really looking for m and I'm really looking for b. M, of course, is the slope, b is the y-intercept. Do you think you can pull out some information and get the line? We can start with the point slope form if you like. I'm just trying to solve on the side. Okay, I think I have the answer. That's what do you think? Equation of the tangent line, and everything is at 5. Okay, that we know, everything is at 5. And g, the value of the function at 5, it's -3. That we definitely have point. And what this means, g prime at 5 is 4. Oh, or maybe I can ask you the other way. Okay, let me write the point slope. Maybe this will be easier. I mean, either way, we will end up with mx plus b anyway. Okay, who can tell me what is the slope? What's the slope of my tangent line? The number is on the screen. The answer is on the, yes, thank you. This is 4. Because slope means derivative at 5, and this is 4. Excellent. That means this is, of course, my point 4. I can maybe write, not 4. Everything is happening at 5. Okay, x is actually 5. Okay, and now I just need the corresponding y value. What's the corresponding y value for x5? Oh, of course, yes, g at 5 is -3. Okay, that's we done. Negative and negative, I mean subtracting negative is positive. Distributing 4, I'm getting this. That means it's 4x minus 23. That's what I was looking for. Okay, but I can tell you that again the point. This is the important part. Slope of the tangent is just the derivative. Okay, I can circle the blue. That's what I want you to remember. Okay, let's see. I have another one, but we can skip this one and we can, shall we skip this one? Okay, let's skip this one. Oh, maybe we can get this one, because this one is nice exam type question. That means let's answer this question as a last one for this section, and I will still cover section 2.2. Okay, that we do have a function f of x on the graph, and we have function g of x. Okay, and now we have to calculate h prime at 4, but h is defined just as a difference. Okay, that's we have to find, probably we have to find f prime at 4, and we have to find g prime at 4, and then I will subtract the numbers. Okay, that's me now. The question for me is, what is f prime at 4? Who can answer this question? If you can really answer this question, you perfectly understood everything what I said. What is f prime at 4? Looking at the graph. Oh, yes, Matthew, thank you. It is 0. Because, of course, this means slope of tangent at 4. That means this is 4, and I'm looking for the corresponding value here, and just the horizontal line. Horizontal line has the slope 0. I can write this one more time. This is 0. Okay, using exactly the same concept, can you tell me what will be g prime at 4? G prime at 4. G is the other function. I think it's 2. I can possibly use different color. This is the corresponding value, and oh, it's just the line. I just have to find the slope of this line. And I think it's 1, 2, 3, 4, 2, 4 over 2, it is 2. And if we have subtraction, we can simply subtract 0 minus 2, it's negative 2. It's just additional thing. This is important for me. And that means I can maybe write slope 2. That means, please remember, derivative means slope of the tangent line. Slope of the tangent line means derivative. Okay. That means now let's look at this. Derivative as a new function. Because what we did so far, we defined the derivative as a slope of the tangent line, which is still, oh yes, this concept still stays, and it's important. But in this section 2.1, we did define as a finite number. Yeah, like I can even come back this. Derivative is 0, derivative is 2. We had previous problems. Derivative was 5, 6, 7, 1/2. Was a finite number. But now what I will do, I will simply change the value a for x. Okay? Actually, one of the questions we did, that the derivative was 2a minus 8. You remember? You were computing the values. That means now what I will do, not even putting a, I will actually put the variable. That means I will define a derivative as a new function. That means I can say for this question, I think was question 6, the derivative of x will be 2x minus 8. But let's see what we can do. That means having our definition, derivative at the point A, okay, I will simply let this point, like instead of being a fixed point A, I will let this point vary. Okay, which means instead of A, I will simply put x. X, 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 x plus h, x plus h. Okay, and x, oh, x. Okay, that means that's the same thing. Yes, like almost the same thing, but instead of a, instead of the fixed constant, we actually have x, the variable. That means the number a can vary, which you can even think a can, even having a, we can think a can be any number, but a is a fixed number, constant. X is a variable. Okay, that means this is a definition of the derivative as a new function. Because now what's happened, I'm gonna compute the derivative and my final answer is gonna be in terms of x. I will get an answer in terms of x. That's the reason that we're calling a new function. Derivative as a new function. Okay, and a few comments. Of course, we have to assume that the limit exists. We just call derivative because it's the new function we call derivative because it's kind of like derived from f, we will still geometrically, we will still call this new function as a slope of the tangent. Okay, please remember, we're still calling derivative as a slope of the tangent, even if it depends on x. And yeah, it's derived from the limit operation. And in terms of the domain, not always, I mean, sometimes we do have domain of the function and domain of its derivative the same, but sometimes the domain is a little bit smaller because applying this whole process, we kind of like minimizing the values of x that making sense for the new expression, new function. Okay. Okay, that's me now. We can try to find the derivative, okay, the formula, because now will be the formula, f of f prime of x for function x. That's me what I did. Did I type the solution? I don't remember, but I don't wanna, okay, I did type the solution because of course what I can do, I can start with my definition. That's the definition of the derivative. F of x plus h minus f of x over h. But before I do this, it's just a few steps. Do you think you know what's the derivative of the function x? What is the derivative of the function f of x equals to x? Okay, it is 1. But now, another question. Can you tell me why this is 1? Yeah, that's the thing. I mean, you can type. Please take your time. I can give you a few seconds. Okay, any other ideas? Okay, I don't want to be so excited, but yes, that was the answer that I was looking for. That's what actually I just taught you for the past 50 minutes. I know that some of you are thinking about some formulas that you learn in high school, but we don't understand them. Yes, the derivative of x is 1 because slope of this line. Okay, if I will draw a line x, this is x, y, this is my function. Slope is not changing, slope is 1. And this means derivative of the function. Oh, my writing, it's a little bit. F prime of x is 1. Okay, that's what I would like you to know. Thank you for answering. I don't know the name because it looks like some nickname, but thank you. That's the reason. The derivative is 1 because slope of this line is 1. It's not changing. Okay, but let's see. I can do my calculation. F of x plus h is simply x plus h because I have to replace x with x plus h. F of x is x, cancelling out this, cancelling out everything. It is 1. That's mean even using a limit definition. Okay? But please remember, it's nice too. That means, can you tell me for the function, oh, y is gone. What is the derivative of the function 2x? Of course it's 2, it's just the slope. What's the derivative of the function x over 3? It's 1/3 because it's 1/3 x. It's just the slope. Yes, thank you. Okay, that's mean please always use this. It's so excellent concept to be faster, okay, and to be a little bit smarter. Of course, I can't really ask you this. X squared. What's the derivative of x squared? We still don't know. I know that some of you, I know, but how do we know that? Because this answer depends on x. This answer is not constant. Function parabola x squared has different slope at different numbers. That means, of course, it is 2x. And actually, okay, that means let's try to prove it that is 2x. Definition, evaluation, a function. That means instead of x, I will put x plus h squared minus x squared, expanding x plus h squared, cancelling out x squared, factoring out h. And now the 0 is gone. This is 0, 2x. Okay. I know that most of us remember from high school, but we have the process and we know how to do it. Okay, that means this one, this is definitely a new function. This one depends on x. That means if x change, the slope change. Okay, and I do have x cubed. Do you think can we do x cubed? Do you know what's the derivative of x cubed? Of course, but let's see. The definition. And please remember, please take time to actually know how to get the derivative through the limit definition. Evaluating a function for x cubed, we can see x cubed, but x plus h. Expanding x plus h cubed, cancelling out, factoring out h, cancelling out h. And now h is 0, h is 0. The final answer is just what you gave me, 3x squared. Okay, you probably saw section 2.3, which really is showing you the shortcuts. That means if I am not asking you to use the limit definition, please do not use it. If you know the derivative right away, of course we will use the ready derivative for us. Okay? But I still want you to know the limit process. Okay, and let's do one more. Or maybe not this one. You can check this one later. No, not this one. Oh, okay, square root of x. I just want, because this function we're using a lot, root x, and I just want you to know the derivative. Okay, that means, do you know the derivative of the square root of x? We will, of course, we will get the formula. Yeah, it's a little bit different. Oh, no. Oh, 1/2. Yes, 1/2 root x. 1/2 root x. But, oh yeah, this the 1/2 x to the negative half is also correct. Okay, that's mean you know the shortcuts. But let's use the limit definition. This is the definition. This is the evaluation for the x plus h, square root of x plus h, square root of x. And now we remember the conjugate expression, multiplying, foiling the conjugate, not distributing h in the denominator. And then now the h is gone. And now I can substitute for h0, square root of x plus square root of x, 1/2 root x. That means it's really worth to remember that the derivative of square root of x is 1/2 root x. Okay, remember that moment. Example number 6, section 2.2. Because probably I will be using a lot. Oh, what's the derivative of root x? 1/2 root x. Okay, one more thing, because we can focus on the domain here. Domain of the square root of x is simply all of the positive numbers, including 0. But now, domain of the derivative, it's also positive numbers from 0 to infinity, but not including 0, because suddenly the square root is in the denominator. That's what I was trying to explain, that sometimes the domain of the function could be a little bit smaller. We had 0 here, we don't have 0 in the derivative. Okay, so now let's look at few other properties. Oh, I do have a function, but we don't really have to know the graphs. I mean, we know the graph of square root of x. We don't have to know this one. Okay. Oh no, we will not go through this. That's too much. Okay, now I would like to show you different notation for the derivatives. That means we know that we can have f prime, y prime, because that's the traditional notation. We can also use different notation, which looks like this, dy dx. Okay, you probably saw this. If you didn't really see this notation, we may have this. That's what this means. Theoretically, this means d means like a derivative of the function y with respect to x. And this fraction bar is not, I mean, the whole thing is not really a fraction. We will use this notation as a fraction at some point, but we will call differentials, dy and dx. But for now, this means it's just one thing. It's just the derivative, dy dx, derivative of the function y with respect to x. We may use notation like that, which is almost the same, derivative of the function f of x with respect to x. Or we can use something like that, derivative of f of x. Or for the like a multiple variable, we can say derivative with respect to x of the function f of x. And especially if we will have function which depends on x, y, z, then we have to specify it. But for us, it's just this. But I can tell you, probably this, and this are the frequent notation for us. Oh yeah, we call differentials. And if we would like to evaluate the derivative at the given number, we can just say this, derivative of the function y with respect to x, and then at the end, we have to substitute a, or the same notation. Because if we have this is easy to place a here. Okay, for this one, I can't really place a instead of x. I have to indicate that this is derivative and the a value. Okay. Now, what we have? We can say, yes, because this is a statement. We just learned that the derivative is defined as a limit. And we know from chapter 1 that the limit could be undefined. That means if the derivative exists, which means the limit exists, we will call that the function is differentiable. Okay? That means if the derivative exists, because we may have a situation that the given function doesn't have derivative. Derivative is undefined. Okay, that means function f is differentiable at a if f prime at a exists. If the derivative, if the limit is defined. And now we can say the function is differentiable on the open interval, or actually on the n interval, from negative infinity to positive infinity, from negative infinity to a, from a to infinity, or maybe from a to b, just the fixed numbers. It's differentiable at the whole interval, if it's differentiable at every single number in that interval. Of course. Quite common, common sense. Okay, this is the first box is important. That if the limit exists, if the derivative exists, then function is differentiable. Okay, let's see a few cases that function doesn't have derivative. Okay, first of all, let's find an interval, like where is the function's absolute value of x differentiable. Okay, that's me. What do you think? Okay, I do have the solution, but I don't want to give you a hard time. I can draw this function. Okay, this is absolute value of x. I can, and we know that absolute value of x can be defined if x is positive. Okay, if x is positive, it's simply x, because absolute value of the positive number is positive number. Okay, now, if quantity inside is negative, I will make it positive, because this is negative and negative is positive. Okay, that we have this two functions. This is simply x, and this is simply negative x. That means, what do you think? What will be the derivative just on this part? Just for the positive, what's the derivative of x? A 1, okay, thank you. What's the derivative of negative x? Negative 1, of course. I can write this 1 and negative 1. For x positive, it's 1. For x negative, is negative 1. So nice, easy. But now, the problem is point 0, this one. That means what exactly, what will be the derivative? I can maybe write this. Derivative of the function at 0. Okay, that's what we can do. We can try to use a definition, because definition will definitely show me that this limit is undefined. And let's maybe do it, because I would like you to prove. I mean, to know that this is, I can tell you the derivative at 0 is undefined. Okay? But let's see if I can show you a little, not long, really short, using a definition. 0 plus h, f of 0 over h. That means function is defined as an absolute value of 0 plus h minus absolute value of 0. Of course, that's funny. This is simply absolute value of h over h, as h goes to 0. And we did solve similar integral, similar limit in section 1.6, because now what we have to do, we have to split for the left and for the right-hand side. Left-hand side and the right-hand side. And the left-hand side will give me -1, and the right-hand side will give me +1. That means this -1 and this +1 has nothing to do with the green one. That's a different thing. It's just a coincidence. This is telling me that the left and the right-hand side limits are different, which means the entire limit is undefined, does not exist. If the limit is undefined, derivative is undefined. That means please always note, look at the graphically. Graphically, this function at 0 has like a sharp corner. It's changing the direction. That means always when you will see the sharp corners on the graph, at these points, function doesn't have derivative. We can also think about tangent line. Like how can I draw at this green dot? How can I draw a tangent line? Like, I don't want to mess up. Let's say I have this corner. Like, is this a tangent line to that at this point? Is this a tangent line? Is this a tangent line? We can see we can't even draw a tangent line because all of the lines are attached, but they are not really a tangent. Tangent line has its meaning. When I draw a tangent line to the curve, and if I will zoom in, if I will go really, really close, they have to be on, we can't see the difference. But if I will draw any line, and if I will zoom in, I will always have this sharp corner. That means, again, if you see these sharp corners, no derivative at this point, because no tangent, no slope, no derivative. And I did prove based on the limit. That means this function is differentiable everywhere except 0. And I do have some proof. And we can see this is the graph of the derivative. +1, -1, no value at 0. Okay, we can see. Yeah, it's the rapid change in the direction at 0. Okay, that we do have another 2 cases that the derivative is undefined. That means the first one is like a corner, king, we can cusp, we can call, I always call like a sharp corner. Okay, like a sudden change in directions. That means at this point, f prime at a, it's undefined. We can't draw a tangent. That's when we have this shaped corner. Another situation is if we have discontinuity. If we have discontinuity, and sometimes we can even have completely the point could be removed. No point, no, I can't attach my tangent line. Or like, again, the end point is like a sharp corner. How can I attach my tangent line? No tangent, no slope, no derivative. No derivative at A either. And another case is a vertical tangent. Okay, we remember vertical lines has undefined slope. Undefined slope, undefined derivative. Okay, that means that's 3 common cases, common kind of the function that they don't have derivative at the point A. Okay. I have few more things and we will be done. Okay, that's just the sharp point. We can see, doesn't really matter how close I will go, I will always have this sharp point. Okay, I do have nice, important theorem, this one. If function f it's differentiable at A, then it's always continuous at A. Okay, because if the derivative exists, then the function must be continuous. If I will make an inverse of this theorem, of course it's false, which means if I will switch these words, if the function is continuous, then it's differentiable. Wrong, because absolute value is continuous function at 0, but it's not differentiable. Okay, that means the converse is false. And I think that's inverse. Converse means that I am, okay, switching and making, let me put inverse. I think I don't want to confuse you even more. I mean, this is also false. If function is continuous at A, then then function is differentiable. That's the false statement. That's what I wanted you to know. I don't want to go deeper and deeper in the logic of mathematics. Inverse. The inverse, which means we're just switching the words continuity and differentiability. Okay? If the function is continuous at A, then it's differentiable. False. Absolute value is a good example. Okay, and then what I have, I still have few things. Oh no, that's some proof, don't worry. Okay, I have 4 true and false questions. Let's see if you can answer them. Question number 1. If function f is continuous at A, then it's differentiable at A. Oh, let's think about absolute value. It's false, right? Because absolute value function, it's continuous function, but we know sharp corner, yes, is giving me no derivative. That means this is false. What about the second one? If function is differentiable at A, then it's always continuous. Of course, that's true. Yeah, like we can see the derivatives is like more stronger. True. Now, let's look at this one. If the limit of the function exists, then function is differentiable at A. This is probably something from section 1.8, continuity. Okay, but we also have to be really careful, because do you remember the type of discontinuity like this one? Let's say limit at A is 1, and limit at A of my function f of x exists. But actually, one point is removed. That means we do have discontinuity. Even if the limit of the function exists, we may still have this case. That means limit exists, but we do have discontinuity. If function is discontinuous, I can't draw a tangent. That means no derivative. Okay? That means even if the limit exists, doesn't really mean that it's differentiable. Okay, and one more. If f prime exists, then the limit of the function is the same like the value. What do you think? It is true. It is true. And I can actually show you something. This statement is identical like this one. I just use the symbols. If the derivative exists, this means function is differentiable. The limit the same like the value is definition of continuity. Okay, that's the same statement. But of course, it's not easy to realize. Okay, nice. This is actually the picture for free. Nice statements. Okay, let's see what else I have. Let me just, okay, I have I have 2 things. And we will be done. I need 5 minutes, okay? And thank you very much for staying with me. Okay, that means this one, I would like you to give me the x values at which function is not differentiable. That means who can tell me? Let's start from the beginning. And let's assume that actually function it's going to the infinity both ways. Okay, that's what is the first value of x that this function doesn't have derivative. Okay, f prime at -2 is undefined. Okay, what about the next one? -1, okay, I can write this way. And another one, 1, yes, f prime at 1 is undefined. And another one, 2, because we do have this continuity. And 3, f prime at 3. That means all of them, derivative is undefined. I will ask you one more question. Okay. Who can tell me what is the derivative at 4? F prime at 4. Can you tell me the value of f prime at 4? 0, thank you. Is the horizontal 4 is somewhere here. Slope is horizontal line 0. Thank you. You understand. I'm so happy. Okay, and then I have just one more thing to tell you. This is the notation because what's happened? Having a derivative as a function, as a new function, I can take this new function and I can differentiate again. That means having f prime, I can differentiate again and I will have a second derivative. I can also differentiate another time and I can have the third derivative. That means I can differentiate as many times as I want. Of course, at some point I will get 0 and I have to stop. But depends on the degree of the function, depends on the function. Some of the function you can differentiate infinitely many times. Okay? That means this will be like f double prime, f triple prime will be the higher level, higher derivatives. This is the notation using dy dx. That means this is the first derivative, dy dx, and we have to differentiate again, derivative with respect to x of the first derivative. And I know that sometimes this notation is a little bit confused, but this means the second derivative, y double prime or f double prime. That means this means that I took the derivative twice. It's also not really a square. I took the derivative twice, and twice was with respect to x. Okay, but we don't really have to. We will use dy dx, but we will occasionally use this notation. Okay, and one more thing, because I don't wanna. Okay, that we remember that taking the first derivative of the position function, we have the velocity. Okay, now since we can take another derivative, do you know what's the name of the derivative of the velocity? If I will differentiate the velocity, the rate of change of the velocity with respect to time. Do you know from physics maybe, or from different acceleration? That means this will be the acceleration. That means acceleration is the derivative of the velocity, which with respect to the original function, position function, is the second derivative. Second derivative will give me acceleration. And we can also take the third derivative, which means I can also take the derivative of the acceleration. Do you know the name of that? It's a little bit weird, like force. The third derivative, which will be the second derivative of velocity and the derivative of acceleration. I can show you the third derivative, we will call like jerk. It's like a sudden change in acceleration. But this is just for the information. Okay, that means this is derivative of the acceleration with respect to time. Just in case if somebody will ask you to compute a jerk. Okay, and I believe this is my last slide. Okay, that means thank you very much. I know that the session is a little bit longer today, but was really nice introduction. And what you can do, check the session 2.3 and 2.4 on Canvas. Okay, you will see some nice shortcuts for the derivatives, and you will see 2.4, you will see the derivative of trigonometric functions. Okay, and please post any question, like please answer the question if somebody else is posting on Canvas, on the discussion board, because based on that, I will assign at the end of the semester the participation points. Okay, okay, thank you very much for now, and good luck with your week 2 assignments.